So thanks everyone for coming today. Um, our speaker today is Amanda Coston, a PhD student in machine learning and public policy at Carnegie Mellon, where she works with Alexandra Shuldeshova and Edward Kennedy. Her research focuses on using techniques of causal inference and transfer learning to evaluate fairness and the impact of algorithmic decision systems. So Amanda, I'll hand it over to you.
Okay, great. Thanks, Brian. Hi, everyone. Thanks for having me today. I look forward to sharing my work on counterfactual predictions for decision making. And today I'll discuss 3 topics. First, I'll look at how to learn a counterfactual prediction model, focusing on the setting where we have runtime confounding, which I'll describe in a little bit. Next, I'll discuss evaluation of counterfactual prediction models. And finally, we'll get to fairness assessments, and I'll make an argument why it's necessary to apply our counterfactual reasoning to fairness assessments. I'll try to keep an eye on the chat, but I think if there are questions, I think it's just, it would be great just to unmute yourself and interrupt me. That would be great. So algorithms are used to inform decisions in many settings where we want to predict the likelihood of an outcome under a proposed decision. For instance, in consumer lending, in order to decide which loan should be approved, we want to predict the likelihood of default if a loan is approved. And in child welfare, in order to decide which calls to the hotline should be screened in for further investigation, we want to predict the likelihood of harm to child if the case is not investigated. And algorithmic risk predictions are used in other settings like healthcare, education, criminal justice, but today's talk will focus first mostly on child welfare and later on the lending setting. And generally in these settings, the decision maker uses the prediction as well as possibly other factors to make a decision. For instance, in Allegheny County, where I live, when a child abuse referral comes into the hotline, call workers have access to 2 types of information. They get to hear the allegation in the phone call, and they also get a risk score based on multi-system administrative records for all children and adults associated with the call. Call screeners are tasked with using this information to decide whether a referral should be screened in for further investigation or screened out, which means recorded but not followed up on. So note here that the call screener has access to more risk information, namely the allegation in the hotline call, than the algorithm, which bases its risk score on the historical administrative records. So we can graphically visualize what's going on as this decision maker, in this case, the call screener, making a decision T based on factors X, Z, as well as a risk prediction from a prediction model that only has access to features X. In the child welfare screening task, X is then the administrative records containing prior history, and Z is the call allegation. X and Z can both affect the outcome of interest. And so why doesn't the prediction model just use Z as well? Well, this could happen for a few reasons. There may be interpretability or feasibility requirements that prohibit the use of natural language from the phone call in the predictive model. Or in other settings, factors may be too sensitive for use in the predictive model. For instance, Z may be a sensitive or protected attribute such as race, whose use would cause ethical concerns. So we'll revisit this a little bit more toward the end of the talk. But for now, I'll describe how to account for these confounders in the prediction model. And this problem is related to a few strands in the literature, including treatment effect estimation and learning policies conditional on only a subset of features. These methods and this prior work is instructive for our problem, but the goal is notably different. So the focus in prior work was on inference, whereas our focus is on predictions. And additionally, these settings typically thought of a low dimensional X, whereas we want a method that can work for high or low dimensional predictors X. So there's also been work for counterfactual prediction under a different type of runtime confounding due to distributional shift like concept drift. And finally, we'll make use of the pseudo outcome regression results in prior work by my advisor, Edward Kennedy. And so before getting to that, I'll describe some notations and assumptions. So for simplicity, we can think about binary treatments and outcomes, although this isn't strictly needed. It just makes the notation a little bit easier. And then, so we'll refer to our target estimate as nu. And this is the expected value of the counterfactual outcome yt conditional on the available predictors x. We define nuisance functions pi and mu as functions of x and z. Pi gives the propensity to assign the decision of interest t for a case with features x and z, and mu tells us the probability of yt for a case with x and z. And then we make 4 assumptions. We assume ignorability on x and z, but that ignorability does not hold conditional on only x. So these 2 assumptions describe our runtime confounding setting. And then we also assume consistency, no interference between units, and positivity that the probability of treatment t is bounded away from 0 for all x and z. So under these assumptions, we can identify our target as this iterated expectation, where the inner expectation is the observed outcome conditional on x, z, and the relevant decision. And this suggests a 2-stage procedure where we first estimate the inner expectation and then use the output as pseudo outcomes for the second stage. This outputs a final prediction model that only requires x, not z. So as long as all factors that jointly affect the decision and outcome are available in the training data, we can make valid counterfactual predictions, even if some confounders are unavailable at prediction time. Although intuitive, this plug-in approach does not make use of the fact that our target is lower dimensional than the full set of confounders. We can exploit this using doubly robust techniques that additionally estimate the probability of treatment to create a bias-corrected pseudo outcome, highlighted here in green. And so we can use any regression method here, and as long as we can estimate the nuisance functions pi and mu well enough, this approach can achieve up to the same error up to constants as an oracle with access to the counterfactual outcomes. And we would expect this approach to do better than the plug-in approach we saw on the previous slide in settings where pi is easier to estimate than the regression function mu, which may often occur in our settings of interest where we have measured all factors, where we may have measured all factors used by the decision maker, but perhaps not all factors affecting the outcome. So we have these nice oracle efficiency property for this doubly robust estimator, but we still might question whether this approach is always optimal in practice when we want to do predictions. And other approaches like the plugin, or perhaps even an approach that just ignores runtime confounding, might still do well, depending on actually how much confounding you have, as well as the dimensionality of the problem. And so we probe this empirically using synthetic data. Here I plot the mean squared error on the y-axis against various parameters controlling the correlation between x and z in the leftmost panel, confounding in the middle panel, and dimensionality in the right panel. So the doubly robust method in blue performs best or among the best for all settings with non-zero confounding, which is encouraging, but this is just simulations on synthetic data. So for real world settings where we can actually compute this ground truth, it's perhaps best practice to build these models using these different approaches and do a counterfactual evaluation. Here's an example of how we can do that for mean squared error as our evaluation criterion of the prediction models. So we define this error nuisance eta, which is the error of any model nu had. That could be our doubly robust model, or the plugin model, or one that just ignores the confounding. And so it's the error of any model nu hat on x and z. And this is identified under our assumptions, and we can estimate this on a test set using this doubly robust approach, which under sample splitting and end the quarter convergence in our nuisance functions allows us to compute confidence intervals on the mean squared error. And so this is an example for mean squared error, but if you're interested in other classification metrics, like true positive rate, false positive rate, calibration, precision, we give the doubly robust estimators for those in this fact paper from last year. So for more information on what we've seen so far, you can check out a paper on runtime confounding or the fact paper. And I'm going to switch gears to focus on fairness, which is still closely related to the evaluation we just saw. But what we'll see next will draw on the fact paper as well as some more recent work on selective labels. So to recap, we've seen how to learn and evaluate a counterfactual prediction model that can be used to inform decision making. But in these sensitive and potentially high stakes settings, we should pay careful attention to concerns about disparities and inequities that could be perpetuated or exacerbated by the prediction model. I'm going to try to situate our work in the broader field of algorithmic fairness. So for those of you who may be familiar with algorithmic fairness, the next few slides will probably be review, and I hope they aren't too boring. If they are, just bear with me and I'll connect this back to the causal framework shortly. So one question we've already seen surrounds the choice of prediction features. Namely, we saw that settings where it is impermissible or undesirable to use certain factors at prediction time give rise to runtime confounding. And it's worthwhile to note that this question is not as simple to answer as one might like. For instance, in credit lending, we would posit that lending decisions should not be based on race, and the Equal Credit Opportunity Act prohibits that. But companies historically got around this by basing lending decisions on zip code, which is highly correlated with race. So this concern around proxy variables has led to research on how to learn so-called fair representations that contain minimal information about the sensitive or protected attribute, in this example, race. However, it's not clear this is actually the optimal approach, and there's a large body of work advocating for fairness through awareness of the protected attribute. Affirmative action is an important example of this. In a setting with systemic and longstanding inequities, one could argue that it's not fair to be race blind to applicants, since doing so will advantage the applicants who had access to opportunities at the cost of those who didn't because of structural racism. So it's important to be thoughtful about the use of predictive features, but we see that this isn't sufficient to guarantee fairness. We should also analyze the algorithm's impact on key demographic groups. One way to operationalize this question is to look at predictive disparities across demographic groups. So for example, let's consider a recidivism prediction algorithm that has a false positive rate for Black defendants that is twice as high as for white defendants. And we could debate whether such an algorithm should be used in practice, which is exactly what happened following the widely influential ProPublica analysis of the COMPAS tool, which found such disparities in false positive rate for defendants in Broward County, Florida. ProPublica used those disparities to conclude that the COMPAS tool was racially biased. But the story is not quite so simple because false positive rate is only one of several performance metrics we might care about. And by other analyses, COMPAS does achieve parity in calibration. And impossibility theorems tell us that it's generally not possible to simultaneously achieve parities in multiple predictive performance measures. For instance, you can't have parity in false positive rate, false negative rate, and positive predictive value if the prevalence or base rates differ in your demographic groups of interest. So one generally has to choose which metrics are the most important for a given setting. And this choice in part involves consideration of the different costs associated with making different types of mistakes. And this is even harder in settings where the decision is not universally desired or undesired. What I mean by that is in criminal justice, all defendants want pretrial release, and in consumer lending, all applicants want their loan to be approved. But for instance, in child welfare screening, it's not so simple. As we saw earlier, child welfare screening involves determining which allegations of child abuse or neglect should be screened in for investigation or can safely be screened out. And from the perspective of the parent, this is similar to criminal justice. You don't want to be involved in the system and want the case to be screened out. However, from the perspective of the child, it depends on the situation, right? So if the child is in danger, the welfare agency should intervene to help mitigate the risk of harm. So it's certainly not straightforward how to choose a simple performance metric to define fairness in the setting, but we can and should compute the whole suite of metrics to understand where the disparities lie. And we should aspire to do this assessment in a reliable way, but we find in practice that doesn't always happen. So recall that in these decision-making settings, we typically want to predict an outcome that is downstream of the decision, and generally that decision may affect the downstream outcome. For instance, in the child welfare setting, some children, like the child in the second row in this table, could be high risk under screen out, but low risk under screen in if, for instance, the welfare agency is able to effectively offer the family risk mitigating services. Assessments that don't adequately account for this can be misleading. So if we compare the target outcome in blue against the observed outcome, which depends on the decision in the adjacent column, we see a big problem. A model that perfectly predicts our target would look like it made a mistake on the child in the second row. And perhaps, as this table might suggest, this would be more common for boys. So we might mistakenly conclude that the perfect model is unfair with respect to boys. Whereas actually this table suggests there may be some gender-based unfairness against girls, not unfairness in the algorithmic model, but in treatment effectiveness, because screen in reduces the risk for the boy, but not for the girl in the first row. And we can make a more general statement about what's happening here. So observational assessments, which evaluate using the observed outcome Y, tell us whether a model is a fair predictor of who experiences adverse outcomes under the historical decisions. But the question we want to audit is whether a model is a fair predictor of who experiences adverse outcomes under the proposed decision. This is a crucial distinction because this observational approach will mistake disparities in historical decision-making with model bias, and as we'll see in a bit, well-intentioned but naive attempts at supposed fairness can actually exacerbate these disparities. To see how these assessment approaches can differ, let's take a look at what they told us for child welfare screening data from Allegheny County, Pennsylvania. So we don't directly observe the outcome we care about in child welfare screening, which is child harm. And because of this, we have to choose a proxy outcome for our prediction task. Here we use re-referral to the hotline as this proxy outcome. We compare two models, model 1 in the top row and model 2 in the bottom row. And according to the observational evaluation here, model 1 overestimates the likelihood of re-referral in the observed data, and it does so more for Black children than white children. Our counterfactual evaluation tells a different story. Not only does it indicate that model 1 is equally well calibrated across groups, but it also shows that model 2 underestimates risk. Model 1 and model 2 are notably different because model 1 was actually a model of the counterfactual outcome we care about, whereas model 2 was a model of the observed outcome. And so that helps us understand what's going on here, that the racial disparity of the counterfactual model, model 1, under the observational evaluation in the left-hand column, was due to differences in screen-in rates and effectiveness of interventions in mitigating risk. The observational evaluation was confounded by the fact that the outcome for some cases was observed under a different decision, screen-in, than the proposed decision of screen-out. And you might wonder, so what about in settings like lending, where the outcome is only observed under the proposed decision? For instance, you can only default if your loan was approved. Are we okay in those settings to just do the fairness assessment on the set of approved applicants? And you might be thinking that that still doesn't seem like a good idea, because we care about fairness on the population for which the algorithm will be used, which is the full set of applicants. And the approved population is not necessarily representative of the full applicant population. So the fairness assessment on the approved population may look very different from the fairness assessment on our target full population. And this distinction may seem very obvious if you work on selection bias, missing data, or covariate shift problems, and you might hope that this is addressed by algorithmic fairness research. But with a few notable exceptions, that's not really the standard. Instead, it's rather common to develop a so-called fair algorithm, motivating its use in settings like lending, and then running analyses on benchmark data sets like the German credit data, which only contains rows for applicants whose loan was approved. And this disconnect between how algorithmic fairness researchers often present fair algorithms and their empirical analyses in papers versus how the algorithm would be used in the real world can potentially be quite harmful. Specifically, fairness correcting for observational disparities can induce predictive bias when those disparities are due to differences in treatment assignment or treatment effectiveness. So to show this, we can consider an example in which we have a perfect model and observational data in which one group, A, denoted by A equals 1, was historically disadvantaged by either the treatment assignment or the treatment effectiveness. So just for clarity here, I'm returning to the original setup where we're thinking about outcomes under both decisions, but you could go through this process and get similar results for the selective labels setting. And so in this setup, we have by construction parity and performance metrics like true positive rate and false positive rate when evaluated counterfactually, because we are using the perfect model. But there are disparities when evaluated observationally because of this disadvantaging of the group A equals 1. So if we apply a popular fairness correcting approach to try to reduce this observed disparity, we induce a large group disparity in the counterfactual analysis to the detriment of the group that was already disadvantaged. In other words, we are further propagating historical inequities. And observational parities will almost always lead us astray, because the conditions under which observational parity implies counterfactual parity are quite strong. So for interpretation, I'll discuss a set of sufficient conditions for observational parity in false positive rates and false negative rates to imply counterfactual parity in false positive and false negative rates. But the actual necessary conditions, which are a little bit more complex, are given in the full paper. The sufficient conditions include two conditions requiring that there are no disparities in outcomes across groups, as well as two conditions that you can think about as requiring no disparities in treatment decisions. Great, so what should we do about this? Well, if these algorithms are intended for settings like lending that have missing outcomes, then ideally, instead, the process here should be that we develop algorithms that make the relevant adjustments and provide empirical analyses that take into account these data challenges. And this is the approach that we take in a forthcoming work that's available on arXiv, where we use data from a lending institution in Australia and consider differences in average risk score among applicants from historically disadvantaged geographic regions, denoted by A equals 1 here, to applicants from historically advantaged geographic regions. And so this disparity is given on the x-axis, and this is similar to notions of statistical or demographic parity in the algorithmic fairness research. And you would be interested in a metric like this in settings where you're concerned about increasing access to credit in some of these historically disadvantaged geographic regions. We chose geography here as our sensitive attribute because that's one of the main concerns in terms of fairness in Australia. And this plot shows the performance of several models in terms of the AUC on the y-axis and the predictive disparities I was just discussing on the x-axis. So I won't get into the details of how these methods work, but the details are in the paper. But what I would like to emphasize here is that when we look at these metrics among the approved applicants in this bottom panel, this is a set of approved applicants in a held out test set, we might conclude that the yellow triangle method achieves the highest AUC and that the other methods can achieve disparities near zero. But of course, that's not the full picture. So here we had used a semi-synthetic setup so that we could compare against counterfactual outcomes on the full population. And that tells quite a different story. The disparities are generally larger than suggested by the bottom panel, and there are notable differences in disparities across the methods. Additionally, the yellow triangle method does not actually outperform the others in terms of AUC when we look at the full population. Okay, so I was lucky enough to work on these projects with some great people, my advisors, Alex and Edward, as well as Alan, who's a student here at CMU, and Ashish, who's a student at Harvard. And I guess that went a little bit, maybe I went a little bit too quickly. So I'm happy to kind of open it up for discussion or return back if there are any parts that people are curious about going more in depth on.
Thanks, Amanda. That was really great.
Yeah, it was a fantastic talk. That's very impressive work. Thank you.
Yeah, thanks.
And Amanda was very efficient, so we have plenty of time for questions. If Amanda, you might want to keep the slides up, or I guess we'll see how it goes. But does anyone want to start off with questions?
I'll start. I'm worried that I missed a crucial early slide when my kids were screaming and I went to deal with it. But did you define fairness as parity in the perfect model? Or no?
No, that's a good question. So I kind of purposely left fairness a little bit nebulous with kind of the motivation being that some people would argue you will pick so one approach to fairness would be to pick a performance metric you care about, like false positive rates or mean squared error, and say you want that to be equal across your sensitive attribute that you care about. But in our settings, it's not really clear that one performance metric is going to be sufficient. So instead, I kind of advocate for this fairness assessment view where you want to compute all these metrics and just kind of understand the disparities and make a holistic decision based on whether it's unfair or fair.
Yeah, okay, I did get this. I was here for this part. But so then why were you focused on parity in the perfect model later, just as a counter example?
Yeah, so that's a good question. So that is just, that was just like a simple example of why it can be misleading and harmful to do fairness correcting based on the observational disparities.
Yeah, okay.
So we just chose the perfect model because it's kind of very clear to see in that setting. But you could still construct an example without that. And yeah, there's nothing necessary about the perfect model for the definition of fairness. Does that kind of clarify?
Yes, thank you.
Okay.
So once you have selected a fairness metric, then determining whether an algorithm meets your that desired property, or designing an algorithm to meet that, to do well on that metric, is like a mathematical problem. But as you sort of point out, I think the question of choosing a metric or defining fairness is it's like reasonable people could disagree about it. So like, who do you think is qualified, or who do you think has the authority to decide what constitutes fairness for the purposes of public policy?
Yeah, that's a great question. I think, so, I mean, perhaps in the ideal setting, we would hope that a lot of this guidance would come from like legal requirements or come from the government. And I touched a little bit on that. There were things like the Equal Credit Opportunity Act that do prohibit the use of race in lending decisions. But often that regulation is kind of not sufficient, like we saw in the example of redlining, where you use zip codes to get around this, since it's a proxy for race. So then the question is like, yeah, so, you know, you have people like myself who are thinking about these fairness questions, like, but we are probably not exactly the right people to be making these decisions, particularly when it's systems where we're not actually the people who are being affected by it. So I think there's like a lot of interesting work coming out of participatory research design that's trying to kind of more involve the stakeholders and communities that will be effective and help them have a voice in this. I think it's a very like interesting and challenging area because, you know, how do you kind of convey a lot of the nuances and questions here without, you know, then also like influencing the conclusions or opinions that people are going to reach. So I guess that's a long answer to say that I don't really know, but I think that's a very important question. If you've thought about it as well, I'd be curious what you think. That's why I try to take the approach in my research of being a little bit metric agnostic, but just kind of thinking about the right principles and the right frameworks to use for whatever metric somebody would decide.
Yeah, that makes a lot of sense. Thanks.
And I'll let anyone else go if anyone has questions, and then I'll.
I have a question that I might have missed something that touched upon this, but I figured I'd ask it anyway. And like, if this seems like it's taking you off a tangent, please like feel free to not answer that. So one of the things that I was thinking is that you can, instead of operating in the perfect, like correctly specified model, my question is, if you're trying to not induce predictive bias, you might be able to opt for a model space that it's a little bit misspecified and that is like more complex than what you need, where this predictive bias does not end up happening. Does that make sense? So if your model space is flexible enough to accommodate, or it is possible to end up with a model space that is flexible enough to accommodate something that does not have a predictive bias and at the same time has this fairness criterion that you, whatever fairness criterion you opt for. Does that make sense?
Yeah, I think maybe. So are you suggesting like some kind of like constrained optimization approach where you have like, you want to find an algorithm that's still going to achieve like good performance but meet your fairness criteria?
Yeah, and in that you might end up with a model that is not exactly like, is not the correctly specified model. If you're defining the function space to be a little bit bigger than what it should be, you might end up with something that satisfies that concern, exactly like you said about.
Yeah, I can see that. Mm-hmm.
Is that's not where there are impossibility results? I don't know them all off the top of my head, but isn't there an inherent trade-off between predictive accuracy and many counterfactual notions of fairness?
Yes. Yes. Okay. So if the previous question was whether that exists where you can satisfy all the fairness notions, I think your clarification is spot on, that there are these impossibility results that are typically of the flavor if you have different base rates. So in recidivism, if there are different rates of getting rearrested among your sensitive groups, then you can't achieve parity in all the predictive performance measures.
Not
So-
even all of them, isn't it? Aren't they like pairwise impossibility results? I could be wrong because
yeah,
know.
yeah,
Yeah.
But I
you're
think, well, I
absolutely
think
right, yeah.
there is a difference between saying I want to satisfy all the fairness criteria and I want to satisfy a fairness criteria without inducing predictive bias. So I think the former, if you're trying to balance all the if I'm not misunderstanding, and that's like, yeah, if you can clarify, that would be helpful.
Oh, okay. Okay, this is you. I'm sorry. I think there's a little bit of confusion with the term I use. So I use predictive bias here in terms of like demographic bias, not model bias, which might be a little bit confusing. So I'm thinking about predictive bias as telling us about the disparities in the fairness metric we care about.
I think that makes sense. Yes. Okay. Yeah, that addresses my question. Thank you.
Hi.
Oh, go ahead.
No, go ahead, please.
Oh, I was just gonna add, I think it was Betsy who was saying that there are these pairwise impossibility results, and I believe that's right. The one that I always have in mind is this one that you can't have parity in false positive rate, false negative rate, and a positive predictive value. But I think there are some other kind of pairwise ones, or at least the triplets that are kind of the common impossibility theorems.
I learned about these from Dan Malinsky, who's on the call, so he can jump in if we're blatantly wrong right now. But
I just have a big picture question. First of all, a great talk. It's really, really great work. I just wanted to clarify like a high level view. In my reading, or at least like what I've seen from the fairness work, is there's classes of approaches that really focus on how well the model predicts for certain groups versus others. And then there's others that are more concerned with the structural biases and say how the data arise. So say unfair processes and say surveillance or differences in measurement error. And it sounds like to me, is what you're working on more towards the former and less towards the latter? And if it does address the latter, how does the counterfactual approach actually take those other issues into account? At least the counterfactual approach that you're suggesting.
Yeah, okay, thanks for the question. That's a great question. I would agree with your characterization that it's more the former and a little bit of the latter, where so you mentioned that there are a lot of like structural problems that we should be concerned about that will affect the quality of the data. And I think our work is handling one of those problems, but there are a number of other ones, like talked about, like surveillance, or even I guess this is related to surveillance, but that, you know, in a lot of settings, we have only proxy outcomes, and there's like known research has documented that those outcomes are differentially predictive by different demographic groups. So like certain groups are much more likely to be rearrested even when you control for true crime rates. So those kind of measurement errors, you called it, we are not addressing here, although that's a very important problem. So I'm glad you brought that up. The data generating problem that I would say this counterfactual framework can address is, I touched on briefly, is if you have historically you had differences in treatment effectiveness or treatment assignment that were disadvantaged one group versus another. So in this example, it was that you had some intervention, like screening in was useful in reducing risk for male children in the second row, but not for the treatment didn't work on female children in the first row. And so that could kind of, if you're just looking at the data, that can lead to problems. If you're just using the observed outcome, that could actually further continue to harm the female children. So applying a proper kind of counterfactual lens here can address this data problem. But I think there's definitely a lot more work to go to address the measurement error challenges that you were talking about.
Okay, thanks for the answer. That helps a lot, and I really look forward to reading your work and some of the references cited. I don't know if there's an approach that can solve all of the problems that I mentioned, but I just sort of wanted to know sort of where what you guys were focusing on in your work. So that helps a lot. Thank you.
Yeah, no problem. I think my advisor, Alex Sholdashova, and one of our other students, Ricardo Fogliato, they have a paper looking at some of the measurement error issues. I think it was in AI stats like last year or the year before. So you could check that out as well.
Thank you.
Great. Well, thank you for a fantastic talk. I had a couple quick questions. Well, the first one is, you referred to the FACT paper. Which paper is that one?
Right. So
I know it was one of your papers, but the 2000.
That was 2020. It's called like
2020. Yeah.
Counterfactual risk assessments, evaluation, and fairness.
Okay.
I have this. Oh, here we go. Yeah, so this one. I mean, at that time it was called FATSTAR, so I'm not sure that's quite the right way to refer to it, but this is the title of the paper.
I just wanted to make sure I downloaded the right paper. Great, thanks.